So good afternoon or good morning for our West Coast colleagues. My name is Sue Lessica, and I'll be talking today about two topics in the NEAP scopes, RC 1.1 and 1.2. There we go. So these two topics fall under the Advanced Reactor Technologies program. The mission of this program is to identify and resolve technical challenges to enable advanced non-light water reactor systems to deploy. And part of that, of course, are developing materials. The objectives here on my slide list of all the things that need to be done in order to meet this mission. And the two scopes that I'm going to be talking about directly support these objectives, particularly in reducing the technical barriers to deployment and engaging with standards developing organizations to address gaps in codes and standards. And of course, the NEAP program itself supports this technical expertise and capabilities within the national labs and universities. So as I mentioned, materials are a big portion of the research in the ART program, and it includes both the development and qualification of graphite and advanced metallic alloys for these systems. And so on the slide, we have three advanced reactor concepts that have become very much of interest with reactor designers of late: sodium fast reactors, very high temperature reactors, and molten salt reactors. Each of these different reactor types have different designs depending on the vendor, and there's one example here for each of these depicted. So as I mentioned, I have two topics. They're very different from each other. The first one focuses on qualification and acceptance protocols for additively manufactured metallic components. The focus of the second topic is more on graphites and is looking at the effects of irradiation-induced microstructural change in graphite. So let's take each of these topics one by one, and we'll start with RC 1.1. This is qualification and acceptance protocols for advanced manufactured components. So advanced manufacturing, additively manufacturing components has very much become of interest to reactor designers because it enables the capabilities that are not achievable with traditional methods, and including complex geometries, architectured components. And so there's many different ways to do additive manufacturing, and here are some examples on this slide here. Additive manufacturing is a very disruptive technology which can greatly reduce the number of steps in fabrications, which can lead to cost reductions, and future additively manufacturing techniques could also produce architectured materials and that have performance and functionality that we can't even touch with conventional manufacturing processes, which will make our reactor designs more effective, more efficient, more safe. There's a lot of advances going on right now in additive manufacturing components, both within the nuclear industry as well as other agencies and other government other industries. However, because advanced reactor applications are very specialized and they have a very extreme environment, the applications in this area are looking to focus on elevated temperatures, long design lifetimes, and as a result of those elevated temperatures and long lifetimes, time-dependent structural failure modes are of interest and need to be understood. That's creep fatigue and creep fatigue. Also, due to the different reactor coolant environments, the material section is also selection for fabrication is much more limited. There are only 6 qualified materials currently in Section 3, Div 5 of the ASME code. And so how can we address the gaps that are keeping us in the nuclear industry from using additively manufactured components? So in order to use this technology, the components need to be licensable by the U.S. Nuclear Regulatory Commission. And so how do we do that? Just as components that are fabricated with traditional technologies, these additively manufactured components have to meet or exceed the expected properties that were used to design the part. And we need to have an assurance that it's going to meet those properties for its entire lifetime. Due to the differences on how components can be additively manufactured, whether it be powder attributes or the fabrication environment, processing parameters, different microstructures developed and different defect structures developed as a result in the component. So the question is, how do we ascertain that a fabricator has met the contracted performance requirements for these materials? And that is what we're trying to address here. And that is what's needed in order to support advanced reactor deployment. So the scope for this topic, the objective is to develop qualification and acceptance protocols to provide a reasonable assurance that the components will perform as designed. So there's several different things that these protocols can be based on. There's some examples here on this slide, but one thing to remember is that the protocols need to be reasonable within the construction fabrication environment. So we need to understand the relationship between the microstructure properties and performance in order to understand which of the key features need to be characterized and need to be monitored. So the scope does limit us to 2 different types of additive manufacturing techniques, and that's powder bed fusion or directed energy deposition, DED. We also put our focus on alloy 316H, which is a qualified material in ASME Section 3, Div 5. It is also of interest by reactor designers of several different reactors, so it would have a widespread use throughout the different reactor designs. The maximum operating temperature for 316H is 650 C with a 100,000 hour design lifetime. And it would be advantageous if the proposed work could cover both of the AM methods, but it's not required. And also procurement of additively manufacturing technology equipment is outside of the scope of this topic. So now we'll switch gears a bit to the second topic, which focuses on irradiation effects on graphite properties. And so what we know about graphite is that significant changes occur during normal operations. Component dimensions, first components shrink until turnaround when they begin to expand. there's density changes, it becomes more dense, and then it decreases in density, and so on and so forth, as you see listed on the slide. However, there are several bulk properties that have very little change over time due to irradiation. And that's the ability of graphite to be a neutron moderator. There's little changes in specific heat capacity, emissivity, and heat capacity. So what is going on here? Hopefully you can see this, this animation. Oops, I'm sorry. But when irradiation occurs, when graphite is in an irradiation environment, there's a very complex combination of both atomic and crystallographic damage. And so at first, atoms are removed from the crystal structure position, and there's recombination to as you see in the illustration, new planes are added, which causes all sorts of different changes to the microstructure. And so as we have done quite a bit of research on the atomic displacement and effects of irradiation, there's still much more to be done. And it's also important to look on to the next step, and that's the crystallographic damage. So the goal here with this slide is to show that not only do some of the bulk properties change, but they may change differently depending on the different type of graphite. Fine grains versus coarse grains are going to have a different behavior depending on with the same irradiation fields. So how does microstructure affect the properties? And so our first bullet here, we're looking at dimensional change has a great effect to increases in irradiation. However, other bulk properties like coefficient of thermal expansion, thermal diffusivity, isotropity are affected differently. And so the question is, why is this? So the bulk material have different sensitivities to microstructural changes, but understanding these underlying mechanisms so that we can better predict and understand the bulk material's response is what the goal is here. So here's the research objectives for this scope. Research should focus on determining what's responsible for the bulk changes. What are the underlying mechanisms? How is it that the changes due to irradiation in the microstructure are causing the changes within the graphite, within the filler versus the binder? We also need to understand and differentiate between unirradiated and irradiated testing. So understanding the microstructure both before and after irradiation. And there are some properties listed there that are of particular interest: density, strength, modulus, and isotropy. So should any questions come up after this webinar, my information is here, as well as the two technical points of contact, Sam Sham for the additively manufactured topic from Argonne National Lab, and Will Wines from Idaho National Lab on the graphite related topic. And that puts me at exactly 2:15, so we have 15 minutes for questions.
Thank you, Sue. We have Will and Sam on the webinar. I'm going to unmute them now. Will, you'll need to Oh, there we go. Are you there?
I am.
Okay, perfect. Let me get Sam unmuted. Sam, are you there?
Can you hear me?
Yes, we can. Okay, let's move on to the questions. Are only liquid/fusion-based additive manufacturing processes of interest? How about metallic alloy fabricated by solid-state additive manufacturing techniques?
I'm not familiar with that technique, but if they fall in between these two, then we will consider that as a within scope. If not, then we don't, because there are quite a number of different additive manufacturing techniques. So instead of covering all different processes, we really want to concentrate on these two.
Do you have any specified characterization technique in mind?
No, that is sort of a very interesting and difficult question. That the challenge is that how do we characterize the the material in the initial condition and have confidence that the structural response of these AM components will follow what the designers had designed the components for. So after 10 years or 20 years or 30 years. So that is a challenge. And we sort of outline the slides of some brainstorm ideas, but this is what we really would like to have the help from the university community to help us out to figure that out, so to speak.
Materials considered.
Sorry, I think the first part of your question was blocked.
Okay, I'll repeat. Is material for containment structures that are non-metal, for example, made out of cement materials of interest?
No, it's not within the scope of this call.
The focus of this call is 316H.
Yes, and also that as Sue pointed out, there are sort of different reactor developers who have interest in using 316H for different reactor concepts. So in order for us to focus this work, we just want to concentrate on 316H grade, and also that specifically, even though that 316H can be used for high temperature, we want to sort of fix that at 650C, and also a sort of a moderate design lifetime of 100,000 hours, so that the researchers can have a target, so that one can sort of demonstrate the developed methodologies against this type of conditions of a temperature and lifetime, because that as far as the raw metal behavior is concerned, that we know quite a lot about 316H. So therefore that whether or not that we have the ability to have this qualification and acceptance protocol to look at the as printed components, and we have confidence that the protocols can screen out bad components, components that because of various reasons that it won't perform as what the designers has designed the function for that components. So that is sort of difficult part, which is this of the high temperature and time dependence of this type of applications. That how can we sort of be able to take sort of a relatively short-term type of inspections, characterizations, etc., to understand that the components will perform as we expect. So, for example, we suggested that, well, maybe that there's unlike the traditional wrought metal components, that we just use of tensile tests and chemistry check and to make sure that they satisfy the specification. And we would sort of have an idea that's the heat of material will perform at high temperatures and for extended period of time for this type of high temperature reactor operations. But for AM components, that there's a lot of things that we don't know. So we really want to be able to have some means of helping us to have confidence that whatever that we receive, that indeed that it will perform the function. So the sort of the conditions that we lay out is in order to focus the attention and for the PI, so that we have something definitive and something that is amenable within this 3-year program. Okay, Drew, back to you.
Thank you. For RC 1.1, are you interested in certain components, such as coolant tubes or heat exchangers?
We don't have any specific components in mind, and so obviously that is whatever types of typical reactor components that will see sort of coolants will be some of the things that we're interested in, like a sort of piping reactor vessels. So obviously that we don't expect the PIs to bring us sort of a full-size reactor vessel. So some of those scaled sized components, if they go out to the components, so probably that is what we expect to see.
For RC 1.1, does one need to address both creep and fatigue life as the targeted performance index?
Yes, we do, because those are the type of structural failure modes that advanced reactor components will see. So that due to thermal transient, so the qualification and acceptance protocols will allow us to be able to ensure, well, have some sort of reasonable assurance that the components put into service can withstand that type of operational transients. So all those structural failure modes are critical to the function of advanced reactors.
For RC 1.1, are you interested in developing a code case for additive manufacturing as a manufacturing technique?
Yes, ultimately, obviously that we are interested in understanding the technique in terms of this type of acceptance and qualification methodologies. So the ultimate goal is to be able to sort of codify that through either ASME or ASTM, so that people will have a confidence to have fabricators to make a component that can be put into advanced reactor operations. But so the end product of this scope is not necessarily a cold case, but sort of the qualification acceptance protocols that the PIs can convince us that yes, indeed, that if I do X, Y, Z, that I can sort of have some reasonable assurance that these components can perform for 100,000 hours at 650 C under some thermal transient. Back to you, Drew.
So there are quite a few questions. I am going to ask all of them in their entirety, even though I realize that some of them are repetitive. So this is just so everybody can understand that their question was answered. So I'll keep on going, Sam. RC 1.1, does one need to model/test the fatigue performance under radiation in addition to the given temperature and lifetime expectation conditions?
Okay, can I respond? As far as irradiation is concerned, that we're taking baby steps. This is a very challenging problem. So first of all, that we just are interested in having some ability to accept AM components for its for sort of the high temperature surface under mechanical loading or thermal transient. So those are the things. The irradiation performance of the AM components and sort of the corrosion aspects, we will have to defer to sort of future work. So we just concentrate on high temperature mechanical response for prototypical type of operational characteristics in this type of advanced high temperature reactors. Back to you, Drew.
For RC 1.1, how much focus should be on the process parameters as they are now pretty much optimized for 316?
So the scope of this is not in perfecting the AM processes. So in terms of optimization to get that to have the AM process to even be better than the current state of the art is not what we are aiming at. So obviously that if you want to develop an acceptance protocol, you would have to be able to screen out bad components as well as screening in good components. So therefore that we would sort of let that to the PIs to sort of come up with sort of these schemes so that the acceptance protocols will be discriminative. Joe, back to you.
For additive manufacturing of metallic materials, should the work also include testing in irradiation environments?
No. Next.
For RC 1.2, is there a preference of a modeling or experimental lead proposal?
It would be experimental at this point. We just don't know enough about the actual mechanisms, which is why we're trying to focus on the mechanisms before we can actually do the modeling.
Why is 316H the only material of interest?
It is the material of interest for this particular scope because that it has been called out by a number of advanced reactor developers for different concepts. So there's this commonality. And B, that 316H is the materials that we know a lot about in terms of its properties for the raw product form. So therefore that we at least know how it behaves in terms of the raw product form. So therefore that at least that we have certain things to target. And if we have different materials to be sort of look at, it will sort of dilute the sort of the focus of this this scope.
Sam, the same question that Will just answered for RC 1.2. For RC 1.1, are modeling or experimental procedures preferred?
Well, experimental, I think that obviously that the acceptance protocol will involve sort of testing characterizations, and also that if they are sort of additional mechanical property testing to help you to understand what needs to be looked at, so that is all within the scope. And in terms of modeling and simulation, yes, that could foreseeably be one of the players, because that, as I've said, that if you sort of look at the material in is sort of the so-called virgin state, whether or not that, well, for example, that if you have the grain size, you have the defect structures, you make the EBSD map, and et cetera, whether or not that will help us to know that the fatigue performance in 10 years will be what the designers have counted on, is sort of a difficult. So therefore, that I do see that there's certain elements of a modeling and simulations, and also that in terms of some of those institute process monitoring data during the AM process will play a significant role in terms of the acceptance of protocols. And also that, let me just make sure in terms of the 316, there are different grades of 316, and in the AM world, that the 316L grade, L for Larry, is sort of the predominantly 316 stainless steels that people have printed, but we are not interested in 316L, because the 316H grade is the sort of the reactor grades that has the material is qualified. So therefore, that if we can demonstrate that the acceptance and protocols work with 316H, that will really help us to for the deployment of this advanced reactor. We don't have to wait until to qualify a so-called 316L, because it is not qualified. Okay, Drew.
For RC 1.2, is there a specific graphite material that should be focused on?
No. Fine grain, large grain, well, medium, large grain is not really considered a nuclear grade, but medium grained and fine grain, super fine grains, all of those we think should behave similarly as far as the microstructural changes. So no, there's nothing that's specific.
For both technical areas, is there an emphasis or a desire to include DOE NEAMS tools such as Moose or Marmot?
For 1.1, there's no specific preference in terms of what modeling and simulation software or techniques. So, well.
Yeah, 1.2, same answer. There's no need for that, simply because we're still trying to figure out the mechanisms so that you can put them into a model. So no.
Is there still interest in research on alloy 709, like tweaking the formulation?
Yes, we have an interest in that in terms of the DOE-NE programmatic program within the arts program, but not specifically for this RC 1.1 scope.
Is there a list of previously funded atomistic modeling and simulation of graphite radiation damage?
Not readily available, but I can go ahead and try to take a look at that. If people want to get a hold of me personally, go ahead and I'll try to get generate a list they can start with.
And if that list is produced, we will provide that to all applicants.
Okay, yes.
For RC 1.2, is surrogate ion or proton irradiation relevant to simulate neutron irradiation?
Great question. Sure. I think that, why not? We don't know what the mechanisms are. Let's take a look at that. And what we can do is we can compare them with the bulk neutron irradiation and see if there's any real differences. At this particular point, that's probably good enough for a research endeavor like we're trying to do. So yes, that's correct.
What high temperature properties are of interest?
Is that RC1 or 2?
It doesn't specify.
Oh.
For
Well,
RC-1
go ahead.
1.1, it'll be sort of the mechanical properties in terms of tensile, creep, fatigue, and creep fatigue, and also ductility of the material. Well,
yeah, as far as high temperature mechanical properties, graphite actually gets stronger, and the stiffness gets higher under radiation and at high temperatures. So really room temperature is going to be sufficient for any kind of mechanical testing.
Are only metallic materials being considered for AM components? What about ceramics, such as SiC?
only metallic, and for demonstrating the qualification and acceptance protocols, we will only look at 316 H grade.
For RC 1.1, do you expect to perform hipping operation after PBF or DED?
This, I don't know what is the sort of the state of the art. So therefore that it could be as printed, it could be under some heat treatment. So I will just leave that with sort of the standard sort of the state of the art of practice in this in the additive space. Back to you, Drew.
Are you still with us, Drew?
Yes, yeah, sorry. Our Bluetooth microphone or our Bluetooth speaker set is cutting out. So thank you. I'll continue on. We are going to continue on with questions, by the way, until about 12:50. That's about 10 minutes before our next presentation. So for RC 1.2, how much interaction with graphite creep experiments at ATR is expected?
Minimal. The irradiated graphite will be available for anybody who wants is performing research on this. So we have irradiated graphite that in samples that are readily available for anybody. All you have to do is ask, and we'll send it out to you. So, but as far as interaction with the CREEP program, you do not need to go in and put any kind of emphasis on interacting directly with the AGC program. But we do have samples, and we will make them readily available for anybody who wants to do this research.
For graphite, what types of modeling efforts would be within the scope for this topic? Also, how many graphite grades are of interest?
Well, let's start with the second one. That one's easy. If they want to focus on the major grades of graphite in the EGC program, that would be probably the most beneficial, since there's more information in the last 20 years on the 5, 6, 7 grades of graphite that's in the AGC program than pretty much any other nuclear grade of graphite that's been produced in the last 20 years. So focus on the 6 major grades of graphite in AGC, and that would be very good. As far as modeling is concerned, what I would like to do is like I said, I think the emphasis should be on understanding and determining the mechanisms. So it's an experimental approach. But of course, any kind of modeling, once you have that information, is going to be desirable, specifically, basically to scale up. So we're going to be looking at not nanometer, which is the crystalline graphic length scale, but we're going to be looking at the micron, submicrons, if you will, hundreds of nanometers, on up to millimeter length scales. So some kind of modeling effort, once you have a good understanding of the mechanisms, is probably going to be appreciated. But of course, the emphasis is going to be on the experimental approach, so that we can truly understand what is going on at those length scales. All right, back to you, Drew.
Are studies of variations in base composition of 316H of interest?
Let me see if I understand that. So presumably it's referring to the chemistry of 316H. If that is the question, then the chemistry specification of 316H, there's a range. So ASTM and ASME have the chemistry specification. And additionally, for Division 5 applications, that the code has additional restrictions in terms of nitrogen, titanium. So those are the informations that can be obtained from looking at the Division 5. And so we are looking at just any AM fabricated components that is within the this chemistry spec from ASTM, ASME, as well as Division 5.
Is software development of interest in either scope?
Well, let me address 1.1. Software development on by itself would not help us to do acceptance. So if whatever computational methodologies that is needed together with some sort of chemistry testing, characterizations of the witness samples, and mechanical property testing of the witness samples, how to use all these sort of very large data sets that is collected during the AM processes. All of that, the way that I see that will be necessary in order to come up with the sort of credible acceptance protocols that can be used to screen in or screen out AM components. I don't see that solely software by itself can accomplish that. So, Will, your turn.
Okay, 1.2, I think it would be a minimal advantage to look at anything from a software aspect. Again, we're sort of starting from scratch here, trying to understand mechanisms, and then once we do, then we can start expanding out into those things. So basically a minimal advantage for that. Back to you, Drew.
What properties are your target for the qualification? This doesn't have a specific work scope.
For 1.1 for AM, what properties that we target? So currently that for wrought metals, we only do room temperature tensile to accept a heat of material. For high temperature reactor applications, we additionally for stainless steel 304H and 316H, we additionally require to have a fatigue test done, and it's done for stainless steel is at 600 degrees Celsius, and the fatigue test will have a 1 hour hold time, and we require that the material can withstand 200 cycles this creep fatigue without sort of seeing low drop before we will allow that heat of 316 raw metal to be to be used to fabricate sort of high temperature reactor components. So therefore that even for the raw metal that we do have this type of additional high temperature testing for advanced reactor applications. So in terms of the AM, that I think that we are asking the PIs to sort of reimagine what needs to be done. Obviously, that we need more than what we currently are testing for raw metals. So a tensile probably will not be discriminate enough to let us know whether or not that the AM components can sort of deliver that type of mechanical properties performance at high temperature for sort of extended design lifetime. Okay, Drew.
So Drew, let me real briefly talk about the graphite for 1.2. It will be, the focus will be on mechanical properties, physical, if you will, modulus, stiffness modulus, strength, tensile, compressive, flexural. I would suspect that you're going to want to focus on tensile and compressive. They're probably a little easier to understand, and they will all be done at room temperature. There's no need to go in and get fancy and do any kind of elevated temperature at this point. We're looking for mechanisms, so keep it simple. It'll be those kinds of mechanical and you know, elastic type testing at room temperature. Thank you.
Is the graphite irradiation study limited?
I'm limited to what?
You cut out, Drew.
Yeah, you cut out, Drew. I think we'll have to wait for him to come back. Drew, are you there?
Will, did you hear that last question?
I did not. I apologize.
Okay, let me try again.
Sure.
Is the graphite irradiation study limited to structural graphite, or is graphite matrix used in HTGR fuel elements also under consideration?
Great question. Let's focus on just the structural graphite for now. Matrix material, simply because it's not graphitized, it's going to be potentially, well, it does have a different irradiation performance. And so there may be differences in the starting mechanisms that change the microstructure. So let's start on just the structural graphite for now and leave the matrix to another day. Thank you.
Yeah, we're going to try to field one or two more questions before we need to cut off for the next presentation. How will the additive manufacturing work proposed here in FC 1.1 coordinate with NE5's neat crosscut advanced manufacturing program?
The advanced manufacturing program is much wider, has a much wider scope than what we're looking at here. So our focus here is really for developing these acceptance criteria for protocols for 316H because of its focus for advanced reactors. So the AMM program is not currently focusing on this area, and so that's why we took it upon ourselves to look at this because of its direct application for advanced reactors. So there isn't a direct any kind of overlap on what's going on in AMM.
Yes, I want to echo Sue that for this scopes that we are not interested in improving the AM processes, printing different ways and optimizing further the AM process. We just want to use whatever the state of the art. We're more concentrated on how to accept components that are fabricated by these two AM methodologies. Back to you, Drew.
For RC 1.2, would you consider atomistic and/or mesoscale simulations as an acceptable tool to help identify mechanisms?
No, well, not atomistic, simply because that work has been done. There's been a lot of work out there. I'm not saying it's complete, and we still need to do that kind of work. But for this specific call, we're looking at, say, the next link scale up. If you want to take a look at the atomistic and how that influences the microstructural changes at the next link scale up, say at the hundreds of nanometers and submicron, that's perfectly acceptable. But to go in there and just focus on the atomistic models is defeating the purpose of this specific call, which is we want to look at the next link scale up.
For RC 1.2, can destructive measurements be performed on the irradiated graphite samples that are available?
Yes.
Will someone at DOE provide the additive manufactured samples for RC 1.1?
Not specifically. Now, obviously, that the DOE program has sponsored sort of various programs that there could be sort of 3D printed samples that one can ascertain, but that will probably be between the PI and the individual program. So for this call, that we are not prepared to sort of try to supply AM materials.
We are running out of time. We still do have several questions. We will address these questions offline in a written format and release that with the webinar transcripts. Sue, before we leave, could you please show the slide for RC 1.2 again?
This one here, the last one.
I'm not sure. I think maybe we'll show both for about 10 seconds and then we'll call it a day.
Prior one.
All right. These presentations will be available within about a week or so after this webinar concludes. So if you do need the slides, they will be available on nup.gov at a later date. Thank you, Sue. Thank you, Will. Thank you, Sam, for being here. We will pick back up in about 5 minutes with the RC4, which is the TRISO fuel workscopes. We will, and the HTGR workscopes, excuse me, TRISO and HTGR. We'll talk to you soon.
Okay, thank you.
Thank you.